start recording. You guys okay? Want to say?
Oh, I have a question.
Oh, hey. I actually want to start. This is like a homework question?
Yes.
Good.
Well,
I wanted to
Lucas, when
start
did
with
you
that.
get here?
I was having trouble like finding the second angle or second triangle.
Oh, in the ambiguous case.
Yes.
Okay. Do you know a certain problem I can look at here? Looking at page 406, right? Is this off the out of the book or off the worksheet?
Off the worksheet would probably be easier.
Worksheet. Okay. To pull that up real quick.
Like problem 10, I think.
Okay, give me just a second, and I
Yeah.
will pull it up on the other screen, see if we can talk through it. Okay. Let me switch over. By the way, we should be able to watch the video today too, so I learned things. Number 10?
Yes.
Okay, let me go ahead and transfer that over to the whiteboard so we can draw. But certainly it looks like we have two sides and the third angle, right? This is an SSA problem. So I got you on that. Let me switch over to the whiteboard. And let me draw this up as best I can to try to match this. So I'm going to make an angle here of 27 degrees. And I've got, so this is going to be angle K. Side P I'm going to put here at 35. And side K I'm going to put, let me back up and do that with a line there. And I'm going to write it as a dangler because I don't know what it's going to be yet. And this is going to be side K opposite angle K and side P opposite angle P. And then we'll put H here, which is kind of irrelevant, and H there. Does that look okay? Lucas?
Yes.
Did I lose you?
Yeah, it looks good.
Okay, all right. So you're saying you had a hard time finding this third angle. So the first thing we're going to have to do here is check 35 sine 27. Did you do that first? Which means what we're really looking for is what is that length going to be? And I'll get my calculator here. 35 sine 27 is 15.89. So 18 is clearly too big. Can we all live with that? Which means it doesn't actually look like this. It actually looks like that, or it's going to look like that. You good, Lucas, so far? Now, I want to ask you this, Lucas. Did you find one of the angles and then have trouble finding the other one, or was it finding even one angle was an issue?
No, I found one of the angles, but I
Okay, so did the angle you find, I assume it was probably the acute angle like that. And the reason I assume it's acute is because inverse sine will give you an angle in the first quadrant, which is between 0 and 90 degrees. So that's what your calculator will give you. Did you find that angle?
Yes.
What is it?
62.
Okay. Is it good enough to say 62 exactly? Okay. So I'm going to look here real quick. at question 10 and the answers. And I'm going to show you this real quickly, what it says for everybody else to see. So it says 62 or 118. See that? So what I hear you saying, Lucas, is how do you find the 118? Right? Because the other option here is for the side 18 to be here. And we've got this obtuse angle that we don't know. So the way we do that is you have to kind of outsmart your calculator. So we know that a 62-degree angle looks like that, 62 degrees here. And that means that there's a 28-degree angle there between it and the y-axis. Agreed? And whatever the sine of 62 is going to be, it'll be the same sine here at that angle, at that angle. Because sine is symmetric along the line pi over 2. If you want to get real nerdy here, we can do this. There's our sine curve, right? And this is 0, this is pi, this is 2 pi, and right here is pi over 2. And sine is symmetric on either side of pi over 2. Sorry, 90 degrees. So if I have a 28-degree angle here, then I will also have a 28-degree angle there to create a new angle whose sine is the same as is at 62, and that makes that angle 90 plus 28 equals 118 degrees. How's that feel?
A lot easier than I thought it was.
Okay, well, good. Well, I'm happy to see that, because if we can get over that, that's not going to be a problem. It looks like, as I'm looking at, let me go back to my other screen here. It looks like, looking at this problem, we certainly, questions 1 and 4 just help you identify those two triangles, but then 6 and 10 are the two that show the ambiguous case, where you have two possible answers. And so, oh, no. Yeah, 6 is like that, but it asks you to find the missing side instead of a missing angle, but it's the same kind of problem. So I can see those two being a little problematic. I don't know if anything else here really is that much of an issue. So let me now throw us out to the whole class. Anything else on this worksheet you want to go over, or from the book assignment? Are we totally good?
Can you go over how to, like, number 12?
Number 12 on the worksheet or in the book?
In the book, because just like the things that they give you.
Yeah, let me open up real quick so I can see it. Can I just check one more time though? Are we better than we were on identities? Okay, good. I'm glad. So you're saying, how do we deal with the minutes?
Mm-hmm.
So there are 60 minutes in a degree, just like there's 60 minutes in an hour. So 40 minutes is 2/3 of a degree, 40 over 60. So I would do it like this. This would be, so it's 5 degrees, 40 minutes equals 5 plus 40 over 60 equals 5 plus 2/3 equal, well, approximately 5, 6. So if you look at angle B, That's so funny. That's the only oh, no, there's another couple in there, aren't there? Look at angle B, it's going to be 8.25 degrees. Because 15 minutes is 1/4 of a degree. We talked about this super briefly, I think.
Yeah.
Yeah, so it's very fair to have that question. That's totally fair. Did you do any of the other problems that had that in there?
No, there's one more that had it, but I didn't do it.
Okay, 21 or 22 or
It's 32.
Did I sign that to you?
32?
I did, didn't I? That was one of the multiples of 4, right?
Mm-hmm.
So 25 degrees 4 minutes. That's 25 plus 4 over 60. Was 25 plus 1 over 15. 25.0. I think that's it. So I'm sorry for that. I didn't intend for that to become an issue, and it was an issue. So sorry about that. I don't actually know the value in this book, including that out of the blue, since we haven't worked on that for who knows how long. But if you can get past that, I assume, is everything else okay though with doing these problems?
Mm-hmm.
Oh, that's music to my ears to hear things are okay. So can we move on? Wow, fun. All right. So I debated a couple days ago about doing the whole section in one shot, but I think wisely I thought better of it because I wanted you to be very comfortable with this process of the law of sines, working with just, triangles that look like this before we got into really serious application problems. So today the focus is on applications of using sine, partially the law of sines, but also another application of sine, to solve problems. And we're going to tackle the Frisbee problem here. And I'm going to show you the video again, part of it at least. And I got the video audio working now, so I get how that works. So that'll be a lot better. But what I want to start with is actually a fairly simple idea that will take you back a little bit. That is area of a triangle. And I assume most of you, when I say that, somewhere in your brain, see that formula come up. Area equals 1/2 base times height. And I'm going to draw for you an example problem that illustrates how you would use area equals base times height. So here we have a base of 18. We have a height of 6. Oops. Height of 6. And I'd like to think at this point in a pre-calculus course, you look at that like, yeah, that's a pretty easy problem. 1/2 18 times 6, and we're done. Where this becomes an issue, though, is when I give you instead a problem that looks like this. So give me just a second, and if you want to copy something like this down, you certainly can. This is going to be angle A, angle B, angle C, side A, side B, side C. Great, now find the area. Right, so as we go through this, you're like, well, I know that area equals 1/2. The base is A, and then I'm stuck. And like really stuck, like there's no way to actually figure this out. And so what I can do to make it look like I'm being helpful is I can add numbers to this problem. Great, 97 degrees. 24 degrees, 59 degrees. 15 centimeters, 13 centimeters, and 6 centimeters. So I'll give you a second to update that. But still doesn't solve our problem. Because there's no way that I, based on all this, am going to get this height right there. So what trig does is it gives us a mechanism for finding this height, which is a nice little formula, but it's a crazy cool formula as well. So you have all this written down. I'm going to move on to a new page and just show you things with A's, B's, and C's, and then we'll come back and do this problem. Okay? So I'm just going to copy this exact problem again. Here, here, there. And we had C, B, and just to be clear, it doesn't matter. It doesn't really matter where I put A, B, and C. But what I want you to appreciate is that what's missing right now is this, which we're going to call our height. Now, this is going to look a lot like the dangler problem that I showed you the other day, but we're going to approach from a different perspective. I know I want area to equal 1/2 base times height. So for example, in this setting, it might be 1/2 A times something. Well, we'll put a height in there for now, but that's the thing that we don't know. So how can we come up with an expression for that height? I'm going to pose it to you as a class. How can we use the concept of sine to somehow involve that height h? Everything else in the triangle is a known value. Angles are known, sides are known.
Use sine C.
Love it. So if I put myself right here in the corner C, I can say that the sine of C is h over b. Agree with that? Opposite hypotenuse. So therefore, h equals b sine C. And this is where you should say, oh, we just did this the other day on the ambiguous case. But here's where it gets really cool. If I know that h is b sine C, I now have a formula to find the area of a triangle using only a side, an angle, and another side. It's that SAS setting, which might be useful, might be familiar to you, but it doesn't require that we have to actually go in and find this value. So that's all fine and good, but then you should say, well, great, what if I don't know angle C, and instead I only know angle B? Could I still do it? Well, in this triangle, isn't A still the base? So I can still write the area as 1/2 base times some unknown height. And the question I want to pose to you is, can I express that height now in terms of sine and angle B? And of course, you're seeing the answer is yes. Are you seeing that? That I can express the height h in terms of the sine of angle B? I'm going to write sine B equals h opposite over C hypotenuse. I'm going this direction. Good heavens. Oh, now I've lost my, oh, lovely, I've lost my pen. Kidding me. Literally lost the battery on my pen. This is going to be great. Now I get to do it with a mouse. Let's see.
You got this.
Oh, I got it. I did it. All right. Put it down. Take the battery out. Put it back in. Okay. Whew. So H is going to equal C sine B. But now look what happens. If I put C sine B up here, I have another formula for the area. But I would want you to notice super carefully what I have in these formulas and what I don't have. In this formula over here, I have two sides, A and B, and the sine of the third angle C. I've got A and B and the angle C. Over here, I have A and C, two sides, and the sine of the third angle. You don't think it's possible that it can work for A too, could it? Of course it does. Area can also be expressed as 1/2 BC sine A. So as long as you have any two sides and the included angle. So again, if I have A and B, C is included. If I have A and C, then B is included. If I have B and C, then A is included. As long as you have any two sides and the included angle, you can find the angle of any triangle without having to have without ever having to know what that height is. So now we go back here. And I want to challenge you to try this, but I want you to do it a couple different ways. So I'm going to ask a couple things here. The two gentlemen whose faces I can see, that's Lucas and Damien, I would like you to do this problem using angle C as your reference angle, which means using sides A and B. Ladies who I can see, Monse and Anna, I'd like you to use angle B as your reference angle and sides A and C as your two known sides. And Foster, because I can't see you, I want you to use angle A and the sides B and C as your known sides. I want to figure out what the area of this triangle is. And it literally should take you 15, 20 seconds. So I'm going to go back again and show you the formulas are all two sides, sine of the included angle, and then of course the 1/2 part because it's half of a parallelogram, half of a quadrilateral. So pick where you're at, pick your angle, and you have the other two sides, and then go back and let's figure out the area here. And it should be as quick as one calculation. We'll give you a few more seconds to try it. Lucas and Damien, do you have an answer? Exactly.
No, 38.57 square centimeters.
Okay. Anna Monse? Monse, you got this. Don't just let Anna do all the work. You know she's going to answer, so you don't have to say anything. I'm going to call Monse right now. Did you not do it? Like, you have to take off mute so I can hear what you said.
I don't know.
So here's what you're going to do, Monse. You're going to do 1/2. Remember, this is your reference angle, right? B. So your two sides are 15 and 13. So 1/2, 15, 13, sine 24. A C, and the sine of B. Again, make sure you're in degree mode. Did you get 3857?
Yeah.
Yeah, cool. Foster?
I got a really big number.
Tell me how you did this. Did you do 1/2 6 times 13 times the sine of 97?
No. Oh, I see. Hang on.
Okay. Now, just so we're clear, I'm getting a slightly different answer than the other two, just because I think what comes down to is these three sides and those three angles are really close, but not going to be exactly perfect.
20.79.
No, I bet you're in radian mode. Check your calculator.
No.
So this is what I got right here. Can you see that? 0.5
Mm-hmm.
times 6 times 13 times sine 97. I get 38.7.
Yeah, I got that.
Okay. And my whole point in showing you this is it doesn't matter which side or which part of the triangle you approach this from. It always works. It always works. This is a really cool, slightly unexpected result that comes simply from understanding how to apply sine in a triangle where you don't have a right angle. So this is it's a sort of a three-way formula right there. Okay. Any questions on that? Because if not, then I want to go on and tackle the Frisbee problem. Can we do that? Okay. So let's go back real quick. I'm going to make sure that it is working. It is. And I'm going to show you, I'm going to fast forward a little bit through to the actual Frisbee problem. Okay, let me play this just for a couple minutes, and then I'm going to show you a map, and we're going to lay out this problem, and we're going to solve this problem with the law of sine.
This to you. Off in the distance there, and I'll zoom in a little bit, that's the tennis court right there. And Ivan and Aiden, of course, you've got happy memories from that tennis court right there. And what I wonder is, could I throw this aerobie or a xylo all the way to the tennis court? But I don't really know how far that is. That's one of my problems. So I'm trying to figure out a way that I can figure out the distance from where I stand here all the way down to the tennis court down there. And I think I can do it, but I got to be a little bit creative. So what I'm going to do is I'm going to have you picture a line that's going straight towards the tennis court from where I'm standing. And then I'm going to make an angle and go to my neighbor Tom over there, Tom Patton. Good morning, Tom. And then I'm going to picture the third leg of the triangle being from Tom's house down to the tennis court.
Okay, we get the idea here. We've been there, we've done that. So let's try to solve this problem. Okay, so I'm going to draw up a triangle, and then I'm also going to show you, actually, no, let me actually show you this. This is, let me go back over here real quick. Any updates on Richard? Oh dear, what's happening?
What happened? You okay? Is the baby okay?
Hang on. Okay, so this is an overhead view. Can you see the map here? Okay, this is an overhead view of the area I'm talking about. My house is this one where the little marker is sitting right here where I'm moving my mouse around. And so I'm standing out here on the grass. Tom, my neighbor, is right here. Tennis court's way down here. So you can see it's going to be a really, really long, skinny, odd looking triangle with angles that I can measure at my house and at Tom's house and a distance I can measure here between my house and his. But I can't measure this distance here because it's a really, really big hill. There's no way I can do that. So let's set up a triangle here. And it's going to look a little bit unusual, but just bear with me, and I want you to draw this with me as well. It's going to look like this, and like this, and like that. Yeah, everybody okay with that drawing like that? And I've got some measurements here. I measured the distance to Tom's house from where I was standing was 90 feet. So just for the record, this is the tennis court, this is Tom Patton, and this is yours truly. And I'm trying to solve for this unknown side right there. And again, unknown, not because it's so far, but because it's down a huge hill and I just can't measure it very well. Although one of my other neighbors, who I'll mention just a second, he said he's got one of those laser shooting things. You shoot the laser, it tells you exactly how far it is. So I could actually do this technically with a laser thing, but that's no fun. We're in trip. All right, this angle right here is going to be 160 degrees. And this angle here, I measured at 16 degrees. So that's all I have. There's really, really wide angle at my neighbor Tom's house, a fairly small angle at my house, and then, goodness, a really, really small angle there. What do we do? I want this to be X. So first of all, what I want you to notice is we do have the makings of a side angle pair. We have X over sine 160. You get that? This side right here is opposite this angle right here. So we have a side angle pairing. By far, 160 is the largest angle, and by far, X is the largest leg. But the problem is, I don't have another side angle pair. I have this side measured. I mean, I can put 90 here, but the angle opposite that 90 is this guy right here.
Just add them together to 180.
Right, right. So this is something you may have to do in the process of dealing with these application problems, is you may have to fill in the gaps and show that's a 4-degree angle. 160 plus 16 makes 176. So now we have to sine 4 degrees. So now I think I can do this. Would you take a second, solve that problem for X, and figure out how far this throw is going to be from my house to the tennis court? We'll give everybody a chance to work through this calculation. Basically, all I would do here is multiply both sides by the sine of 160. And that's where I'd stop. I mean, I'd simplify from there. Bless you. Are we getting any answers? Damien, what do you got?
I got 141.27.
141?
Yes. 441.
441. Okay, that's
Yeah.
all right, good. 441 feet. That's what I got when I do this thing. It was a little, maybe I did this all wrong. 441 feet, which sadly works out to about 147 yards, which would be super impressive, but I can't throw a Frisbee that far. Even an aerobie Frisbee, which I can throw pretty far, I can't throw that far. So if I go back here, I want to go back to this for a second and specifically go back to this. My dilemma is that that's too far for me to throw. I can't do it. I thought I could. I'm standing there like, oh, it looks like it's within reason. Maybe I can do it. I can't throw a Frisbee 147 yards. So in the spirit of I'm not going to give up on this, I tried something else. I did a measurement. If you look in, I don't know if you can tell, it's in the lower right-hand corner of this Google Maps screen, there's a little bit of a scale here. It says 50 feet is a certain distance. I walked to my friend Rod's house, which is right here, and I stood right there and I looked down. I did a quick calculation, and I think this is about 100 yards. Now, 100 yards flat with an aerobie is still pretty impressive. It's just pretty hard to do. I've done it before, but not for a while. But this is also a really, really big hill. So I think if I take advantage of the altitude, I can probably get a much longer distance. So what I'm going to do this weekend, I'm doing this for you, just so we're clear. This is a gift I'm giving to you. I'm going to go out and throw Frisbees from my neighbor Rod's yard from right about here and see if I can get it down onto the court. If I can, you darn well bet I'm going to video it and show it to you next time that we meet after tomorrow, because then I can show off and brag. More than likely, I'm going to fall short. I know that I did a practice round a couple days ago, and I got to about 76 yards with not as big a hill, but I'm out of shape. I'm old. I got a lot of excuses for why I can't perform like I used to. But I'm going to try it. If I can do it, you darn sure I'm going to let you know that I did it and try to record it. If I can't do it, I'm either going to lie to you and tell you I did, or I'll show you how close I got with a photo. But I can always just put the Frisbee on the court and then take a photo of that and say, look, I did it. So you may never know unless you see a video of it. But anyway. All right. So I thought that was kind of cool, because that's a kind of question that you might find yourself asking one day. I mean, you want to measure something you can't otherwise measure, and this is a way to do it. All right. Let's look at another problem here. And I kind of think I want to give you two more application problems of this. So let's try this right here. Here is a problem that deals with a helium balloon that's being tethered above the ground, and at different angles, different lengths, and I want to know how far apart the tethers are, which is basically I want to find y here. So all I want you to do is be able to look at this problem. You can sketch this. I'll transfer this to the whiteboard in a second. Sketch this, and then let's see if we can turn this into a law of sines problem. So I'll give you just a couple more seconds to picture it. It's 80 and 40 on the bottom, and then 100 feet on the left-hand side. You don't even know what the right-hand side is. And now I'm going to transfer this over to the whiteboard, okay? So you're going to lose it, but I'll get it back here for you in just a second. So we have one like that, one like that, one like this. We're trying to solve for this side y. This is 100 feet. This is 80 degrees. This is 40. Now, I want to be clear here that these problems don't have to be terribly difficult. Like if you're sitting there like, oh, isn't this just the law of sines? Yeah, it's just the law of sines. But what I want you to build up I want you to build some confidence in the fact that you can take a look at a problem setting, not just a random triangle given to you, and you can make this happen. So, Foster, what's our first step going to be here?
Complete the triangle angles.
Great. What's the missing angle?
60 degrees.
So 80 plus 40 makes 120. We're missing a 60 degree here. And now the thing you're going to look for is this right here. We absolutely have to have that. We have to have one ratio that connects a side to an angle. Obviously, we're going to use this as our other one. So now we can set up 100 over sine 40 equals y over sine 60. And before you do this, I want to point something out. I know that in the lesson I showed you a over sine A and b over sine B and c over sine C. And at that point, it might be easy to think, oh gosh, how do I do A's, B's, and C's? What do I do? I want you to see right now, I don't care what A and B and C are. I just have to come up with two of these pairs, two of these fractions. So I think you can see how I hopefully will just move this up to the top over there. Let's see what that's going to come out to be. By the way, this is a small little calculator issue, but when you're doing these problems, make sure you watch the parentheses really carefully on your calculator. When you do a sine calculation, it'll do an open parenthesis, but won't close it. And if you're not careful, you get some really funky answers because you didn't tell the calculator to do the right thing. So Lucas, what are you getting for y? Are you caught up in doing this problem?
I haven't gotten it yet.
Okay, all right. I'm gonna give you a second to catch up. By the way, I did this the wrong way, like on the calculator without closing off any parentheses. I got 99.8. That's wrong. So if you get 99.8, really watch your calculations. You got it, Lucas?
Yes.
What do you got?
134.7.
100. I believe I've done it wrong. So I will double check. 134.73, yeah? 134.73 feet. Good. So any questions, issues about this? I don't want you to think the law of sines is that difficult. It's really not. It's actually really useful, but it can be a little bit confusing when you're learning how to work with this. All right, one more quick problem and then we'll call it a day. Okay? Here's the last problem. I have this in words. So I'm going to read the words and I'm going to write it out before we're doing this. Two observers are standing on shore. So we're going to call this observer A, observer B, a half mile apart. This is water out here. And they measure the angle to a sailboat. That's probably not a great place for my sailboat to be, so let me move my B guy over here. Whoa!
Is this a lake, a river, or the ocean?
Let's say it's the ocean. Okay? Does it change how you do this?
Pacific, Atlantic.
It changes everything.
It's Goo Lagoon.
It's a game changer. So what we have is we have this kind of problem right here. See that? And there's a couple angles. So angle A, person A, measures 63 degrees. And angle B measures 56 degrees. So, ladies, I would like you to figure out how far this person is from the sailboat. So I'll call this L for ladies. And gentle boys, I would like you to measure the distance from this guy to the boat, and we'll call it G for gentlemen. I think the key here is me drawing this up, this has created a pretty doable problem. Your challenge is, could you start with this and turn it into that problem? That's going to be your challenge. But let's go and try this. We're all able to get 61 degrees here. Okay, obviously, that's what we have to do. Now, while you're finishing up your calculations, I just want to point out that these three angles are pretty close to 60, 60, 60, right? Which means this is nearly an equilateral triangle. Regardless of how I drew it, it's nearly an equilateral triangle, sorry, equiangular triangle, but therefore it's nearly an equilateral triangle, which means all three of these measurements should be fairly close to 0.5. Gentlemen, what'd you get for G?
I got 0.51.
0.51, so
As did I.
0.51. Great, ladies? Anna, you can answer this one.
I got 0.47.
0.47. Okay. I'm not hearing weeping and gnashing of teeth over these problems. Am I not hearing that correctly? I hope I'm
Because
not.
we're muted.
You're muted, otherwise I'd be hearing weeping and gnashing of teeth, yes? Okay, well, so today, I'm just gonna have you do one set of problems. I'm gonna write them out for you here. We're gonna do page 407. It's the same section in the book. It's 40, 44, and 45 to 53. That's the application problems. 55 to 58, if I'm not mistaken, that is true or false problems. Okay, so a fair amount of work, but I want to believe that the work is pretty straightforward now that we got the hang of the law of sines. Tomorrow, I want to meet with you again, and we're going to give cosine its due. And I have another video to show you too. So excited to show you. It's another problem from my yard that I can't solve directly, but that I need, in this case, the law of cosines to solve. So with that, I will bid you a fond adieu. Have a great day, and I will see you